The final chapter in chapter 13, or the final section in chapter 13, section 13.4. We are winding down talking about materials. In the first section 13.1, we talked about gases. 13.2 and 13.3, we talked about liquids. And finally, we're going to talk about solids. So what are some important characteristics about solids? Solids typically arrange they're in a very distinct pattern. And the fixed pattern of molecules in some solids, not all solids, the fixed pattern in some solids is called a crystal lattice. And that sets up perfectly to form a crystal-like behavior like you're similar in maybe types of gemstones such as quartz or diamond. And they have very, very specific melting points. So a crystal lattice is a specific way in which the particles in the solids arrange. Amorphous solids have no fixed patterns in which their particles arrange. They are kind of put together randomly. Think of it like glass. If glass breaks, does glass ever break the same way twice? Not typically. And that's because there is no definitive arrangement of the patterns in glass. Same thing with butter. Butter, kind of, the molecules are kind of there in just a big old blob. There's not a fixed pattern with an amorphous solid. So they range in melting points too, as you can see. Sometimes butter is very soft on your counter during the day, and sometimes it's very hard, and that's dependent on the temperature of the day. Butter can flex very across the board. So when we have two types of solid bodies, they usually arrange in crystal lattices or amorphous solids. One of the two ways in which the particles arrange, in fixed patterns or in random patterns. When we talk about solids, what we're going to talk about is pressure and freezing. And freezing, we really can talk about freezing and melting because we're going from a solid to a liquid. A solid can only be formed from a liquid. It either turns to a liquid or is formed from a liquid. So for most liquids, increase in pressure on the surface increases the freezing point. So if you increase the pressure on the surface of a liquid, you're going to increase the freezing point. Now, water tends to be the exception to this rule. When water freezes with an increase of pressure, it forces it forces the molecules closer together. So pressure and freezing, just a little bit on pressure and freezing. Now, when we talk about solids, we've been dealing with mathematical equations focused on solids. Well, what happens to a solid when it's heated? It is going to expand. It's not going to expand as much as a liquid or a gas, but it is going to expand. And how is it going to expand? Well, as a solid's heated, again, we're dealing with heat, the kinetic energy increases, so particles move faster. If the particles move faster, this causes them to expand when heated. You can think of an object expanding in two ways. It linearly, so lengthwise it expands, and volume-wise it expands. And if it involves the coefficient of linear expansion, alpha, A, it's going to look like this: how much a substance expands in length. Alpha is a constant. Alpha is going to be vary from material to material, substance to substance. Those constants are on page 361 in your book. So alpha is a constant. It's going to change time to time. Change in L is the length at which your substance changes. L is length, and again, we're dealing with meters. And change in T is the change in temperature. So if something expands, how far is a steel rod going to expand between winter and summer? Maybe a good idea to have when you're talking about construction. So that is linear expansion. Alpha is a constant for that particular material. Steel has a different alpha value than iron, than ice, than everything else. L is the length or change in length, and T is the change in temperature. So that's linear expansion, alpha. Our unit for that is 1 divided by Celsius, because we're taking meters divided by meters times Celsius for our alpha values. Or Kelvin, depending what you want to do, but we're talking about a change in temperature, so it doesn't matter. The change for Kelvin or Celsius is going to be the same. So we have alpha expansion, which is linear, and we have beta expansion, which is volume, and the equation is very similar. Beta is going to be a constant for every single volume expansion. That's also on 361. Change in V is going to be our volume. And again, our change in T is going to be temperature. And this applies to when things are heated. So we're going to heat up a steel rod. We're going to see what the difference is. So we have alpha expansion, beta expansion. If we look at this, here's an example. A metal bar is 1.6 meters long at room temperature, 21 degrees Celsius. The bar is put into the oven and heated at 84 degrees Celsius. It is then measured to be found that the bar is 1.7 millimeters longer. What is the alpha value? Now, for the most part, I said alpha is constant, but in this example, we're going to solve for the alpha value. So our change in length is 1.77 millimeters. But remember, we have to convert that to meters. So 1.77 millimeters into meters is 0.0017. Our original length of the rod was 1.67. And our change in T is going to be the difference between 21 and 84. Now remember, it doesn't matter if it's in Kelvin or Celsius when we're talking change in temperature. That's 63. We go ahead and we plug in alpha is equal to the change in L over L times change in T. We plug in those values and we get 0.0017 divided by 1.60 times 63. You end up doing that, and you end up getting with sig figs, 2 sig figs, 1.7 times 10 to the negative 5th Celsius to the negative 1 value for our alpha values. Now, last thing I want to touch on is what is the practicality of this idea. Well, we talked about bridges. Bridges in Minnesota are a big thing. This winter we've had negative 30 air temp. In the summer we might have a 100-degree air temp. So we're talking about a 130-degree temperature swing in substances. You might want to account for a bridge expanding or contracting that much. So what are some common applications? Buildings, concrete and steel expand at different rates. So you're going to want to figure that out. Thermostats, bimetallic strips. A lot of your non-electronic thermostats work with a bimetallic strip where it'll expand or contract, and that will fix your thermostat. And then lastly, there's one application in the human body in which your temperature changes in the human body. Think your mouth, dental fillings. Boy, that would really suck really bad if at room temp they put in my filling, it fits great, and I had a bowl of warm soup and the filling expanded and cracked my tooth, or B, I had a cold bowl of ice cream and the entire filling fell out. That would be problematic. So there are some ideas in which you're going to talk about thermal expansion, buildings, thermostats, and dental fillings and teeth expansion. So just some things to keep in mind. That pretty much concludes Chapter 13. If you need all the equations for Chapter 13, they're on this slide right here. And I'm not going to go further. You can pause the slides right there and copy them all down if you need those. You'll have a couple problems on Section 13.4 tomorrow, and you can be looking at a test sometime next week.